let's take some of this information then on how we get isotope variation, how we explain the variation in global meteoric waters, and let's put it to work. And this is just to kind of remind us about the expectations when we take water. We start at the ocean. Remember, that's our standard. We evaporate that water. The vapor that we create from it is isotopically lighter than the liquid phase that it came from. That vapor just doesn't sit there. We move it along its trajectory. All of our precip has usually its origin somewhere else. And in this sort of stylized diagram here then, we're taking that water on a trip, and as we move it, we're sending it through then the Rayleigh distillation process, right? We have that vapor phase, that vapor-liquid equilibrium here in this cloud here. We move it along its trajectory, and some condensation takes place. Those heavier isotopes begin to fall out. If you get the heavier rain falling out of that cloud mass by isotope mass balance, what is left behind is going to be a little bit more negative because you've removed some of the heavy stuff. And you continue to move it along its trajectory here, and you can see through this process of distillation, we're getting changes in the isotope composition of the storm as it moves along its trajectory. Mostly because you're distilling rain out, and you're removing rain from that air mass, and as it's moving, and it's moving into the landscape, it's also changing in its isotope value. We get to things like mountains. We get some additional effect because we take that air mass, and now it's not flat land. We actually force it up over a mountain. As soon as you force it up over a mountain, obviously, you have to deal with the effects that those mountains have on the air mass, and that's generally changing temperature. So you're changing the adiabatic or the lapse rate at which that air mass is moving over that mountainous terrain. Of course, it's colder at higher elevations. As it gets colder at higher elevations, we have the expectation that we might have an isotope effect. We're changing temperature, all right? So we're not just distilling water out of the air mass, but we're distilling that water out at different temperatures in the lowland versus in the highland. And so the isotope expectation should also follow from that. Snow is going to have a very different isotope value than the rainfall that comes out of that. So we get set up then with a bunch of isotope expectations about what's going to happen to our storm systems as they move along their trajectories and across continents, over mountains, et cetera. And that's really cool because it really sets us up into being able to then look at isotopic variation on continental or on global scales. And the first group that really got very interested in this was the IAEA. They established a network of precipitation collection stations called Gnip, the Global Network of Isotopes and Precipitation. The IAEA is the keeper of these data. You can have access to these data. They are online and they're open for you to use. The cool thing is that they've been collecting in some areas for a long time. So if you don't have the time or you don't have the inclination right away to build your own local meteoric water line, you might be able to go to the Gnip data and actually fish off of that what you need to get started for your local area, because they have collection stations, as you can see, all over the globe. And the cool thing is, of course, this network was not established necessarily to measure hydrogen and oxygen isotopes in precip. I told you earlier, these guys were worried when they started this monitoring of what the radioactive isotopes in this precip was. There was the United States and Russia out there building bombs like crazy, and they were exploding them all over the place. And so what they said is, how do we know what's going into our atmosphere in terms of radioactive isotopes? So they started collecting precip for measuring the radioisotopes. But of course, the benefit of that is we also had the stable isotopes. And so they established this database. And so it's a massive database. It's a really useful one. And if you work on water, you're going to get to know the Gnip data, as well as the data that actually Gabe Bowen hosts on his website here at Utah, waterisotopes.org. Gabe also keeps a lot of archives of precipitation and other kinds of data. So if you work with water, go look at Gabe's website. He's going to be around. You can chat with him about it. But they're really good archives of water isotope data that you might find useful for your research. All right. From that kind of stuff, Gabe has created things like this. This is what the spatial class is actually working with this week. So they're merging data on isotope variation on all kinds of different spatial scales with geostatistical methods for actually creating these kinds of things that we call isoscapes. So basically, this is a geographical isotope landscape, and you can see here that Gabe has created an oxygen isotope for annual weighted precipitation for the globe here. And he gives us a chance to see now what our expectations would be if we went to anywhere on the globe of what we might expect to see in terms of an oxygen isotope value in the precipitation collected at these various regions around the world. So people are now taking a lot of information and providing these different data layers that you might find useful if you actually work on organisms that, say, may move across these different areas. You've got some isotope expectations. Gabe and his group have been doing a lot of this work. Yeah.
So if you also mapped like the hydrogen isotopes
Mm-hmm.
and they showed different patterns, like how would you, does that happen? And is there like, are there processes that maybe would influence one and not the other? And like, how do you kind of deal with that?
Mm-hmm. It's a good question. Generally, when we create an isoscape for oxygen and we create the same sort of isoscape for hydrogen, we get pretty darn good matching, all right? When we don't get good matching, generally those departures in what the oxygen and the hydrogen actually show us are caused by local features within the area where that precip happened to be collected. So all of a sudden, you throw up the Himalaya, all right? And you get this really steep gradient, and you get monsoon precipitation, or lots of snow, or you get all these other additional temperature effects. Many times, sometimes when you actually look at the exact matching between the hydrogen and the oxygen isoscape, they don't match because many times of those geographical features, or what we'll talk about here is some continental features that lead to some additional little local isotope effects that cause perfect, they're not perfect, but they're departures from each other. They don't map perfectly onto one another, all right?
But shouldn't you see a shift because oxygen is simply heavier, so the heavier will be closer to the shore?
You do see that sort of a shift, but sometimes you can see departures that are a little bit more than what that shift, the expectation for what that shift should actually look like. Okay, so we can take these maps and we can start asking then, if we go back to the processes that we're talking about, let's look at what are the processes that we actually haven't touched completely on yet that explain some of the oxygen and hydrogen isotope variation out there on the planet. I've alluded to temperature, but these data actually show you the temperature data. All right, there's a couple plots here, the early data plotting the oxygen isotope composition against the temperature at the site where that precipitation happened to be collected. So this comes from a very, very milestone paper that anybody who works on water, go read Donskar's paper from 1964. It's beautiful. It has all the theory in it. He really develops a lot of the first global relationships between precip and a bunch of other meteorological variables like temperature, like humidity, things like that. And what Donskar showed us is that we get this very, very nice relationship, very predictable relationship about what we'd expect the isotope composition to be if we knew what the temperature is at the site where we actually measure that precipitation collection. Rosansky took the kind of things that Donskar showed us, and he actually did a little bit of parsing of it. He breaks it up a little more finely. So in Rosansky's paper, it came out in 93 and another one in 97. You can see that he's now added a couple other layers of detail here. Here's that little curve up here in Donskar's data. Well, now you can see what Rosansky's done is he said, that little departure from the same slope happens to be a bunch of marine stations. The ones that are below it are continental stations. So maybe they're being influenced by either local coastal marine effects more if your slope is one differently than if you happen to be in continental areas. So coastal regions, of course, are much more temperature ameliorated. That's why we all live there, right? And continental regions are different. So he basically, what Rosansky did is he said we can kind of parse out the temperature isotope effects differently depending on where we are on the planet. And so if you go to Rosansky's paper, you can also sometimes pull out of there some very nice simple equations that give you a predictive framework of what the hydrogen and the oxygen isotope composition is in a particular area on the planet if you also know the temperature. And you usually do, because there's generally a meteorological station there. You can extract that from the MET data. Now you've got a way to actually predict what your isotope expectations are for that particular site. So mine the data out there. The people have been working on this stuff for a while, and they not only have the isotopes, but many times they also have all the other metadata, like the temperature, the humidity, the elevation, things like that. And that can really be super useful for you as you're starting to explore where you might actually want to go collect your samples. You don't have to do everything. There's a bunch of this background data that actually exists out there. So temperature effects obviously are something we have to pay attention to. Amount effect. This is a very important one in areas that see high amounts of precipitation. This is a really interesting plot of data collected in New Delhi, and you can see here, again, this comes from Rosansky's paper, just to kind of demonstrate for us how when you get into seasons of the year, when you have very heavy rainfall, that you can get some pretty radical departures in what the isotope composition of that rainfall actually looks like. So let's just look at what these data are showing us. Here's the 018 data right here. All right, and what you can see is we've got really kind of stable oxygen isotope values of the precip here when there's very little rainfall. All right, as soon as we get into the monsoon season, when rains really begin to fall, you get really high amounts of precip input, and look at what happens to the oxygen isotope values. They take a very negative departure in the times of the year when you get heavy rainfall. You're just looking at excessive distillation, right? You're distilling more and more and more of the isotopes out of the cloud mass. And consequently, you're getting a departure in the isotope values of the precip that you're actually collecting on the surface of the ground, all right? So that amount effect gets manifests itself very nicely in areas where you get high amounts of precip. So if you work in a seasonally variable environment, where there's a wet season and a dry season, or you have to work in a monsoon area, get your fanny out there and collect this data here, because these amount effects can really be very important in explaining the variation in the isotope values of your source water inputs into this particular area. People that work in areas where there's monsoon rains, this is particularly important. Yeah?
Is it also possible that you're getting a difference in the isotope because the monsoon rain might go into a different place?
Exactly. So we're going to get there. So you again, you're a step ahead of me. We're going to get there. No, perfect, perfect. You're anticipating one of the next slides coming up. So you're right. There are these rain out effects, but you may actually get different source areas as well. And so we're going to look at sources areas in one of the next slides coming up. That's a good question.
So the very effect of the I don't know, the energy in the storm itself, so how violent the precipitation is, like a mist versus a monsoon?
There can be some differences there, and also if you get hail that falls out of a storm, you get really goofy isotope effects, because you get, and in fact, if I think, Darren, you had a slide one time that you gave me where they actually looked at hailstones, and they got isotope variation as you went from the rind of the hailstone inward, because as it was falling down through the cloud mass, it was actually accumulating different sorts of isotopes as on its journey down through, and so the hailstones can also reflect something about the thermal history and the movement of the water actually through the storm itself. It's really, really cool. People have done some of those measurements. Okay. Continental effects. These are things particularly for those of you that work on migratory animals that might move from one region to another, and you might move from coastal regions to continental regions. You might get really concerned about where your organisms are moving. And when you move to continental interiors, you tend to see both oxygen and hydrogen isotopes become more negative. And that's because of principally two things that we've already talked about. Rain out effects, as the origin of the storm moves mostly from coastal region to continental interiors, you're raining out the heavier isotopes. That means what gets left behind becomes isotopically lighter. So continental interiors tend to be lighter precipitation values, but those are also tend to be colder areas. And so colder temperatures, greater isotope effects, more negative isotopes. So you can expect that in continental interiors versus coastal, that's going to be very different. If you work on a migratory bird and it spends its time maybe feeding near the ocean, but maybe raising its young in a continental interior, well, you can expect to see that the oxygen or the hydrogen isotope values of the feathers that they're producing at those different parts of their migratory route might actually be different. That's a tool. Use it. You know, just know that you have these kinds of data. That might be a really cool bit of information that you could use to inform the questions that you're actually asking. So these kinds of things can manifest and play themselves out in a really nice way in the questions that you might be asking, particularly if you work on animals or humans, we're animals, I guess, that move around a lot. This kind of stuff can be really, really important. I saw a hand kind of edging up here. You did? Okay, good. Way to go. Okay. So this comes into play in this single plot here. This is really a cool one, where what Gabe has plotted for us here now is the weighted average of the oxygen isotope composition of the precipitation collected at a particular location. So what he did is he went out there and he got the data for every station. Each one of these are stations in different parts of the globe, all right? And they collected every precipitation event. They analyzed all those events and they took an average based on how much fell there. And that's what each one of those data points are. And then what Gabe did is he plotted it as a function of both elevation from sea level, the dark black line up here, up to higher elevations as you come down. So these isopletes here represent going up in elevation, all right? And as you go from the tropics, here's the equator right here, to the poles. Doesn't matter what hemisphere you're in, right here. This is the absolute latitude. But this is really cool because look what he did for us. He created us a polynomial regression where now we have a predictive framework of what we expect to see the isotopes and precipitation to be if you know the elevation and the latitude of your site where your precipitation collector is. Hallelujah, thank you, Gabe. All right? He came up with a really nice model here for helping us kind of go anywhere with this one regression and kind of get going on what our expectations. And he has this both for hydrogen and he also has it for oxygen. So we could go to somewhere like where I went on a hiking trip recently, Banff and Jasper in Canada, and you can see that in that one latitude, we could go from high elevation, so 2,000, 3,000 meters, down to sea level. You know, if we went in this particular latitude here, and this is the kind of variation we can expect from high elevation to low elevation at that particular kind of latitude. So it gives you kind of a way to understand what the universe looks like out there of isotopes and precipitation. So if you go to Gabe's website, again, isotopes.org, I think he continues to update this. So there's this regression that we see up here. It's slightly modified, depending on the new samples that are coming in. So he's always trying to keep it updated. And that you can actually go in there, and I hadn't realized this about his data. I should have. John, you probably knew this already. You could actually parse it out by decade and things like that. So if you're like working on tree rings, we got some tree rings people in here. You may be interested in, say, pulling out a particular decade that you're collected your tree rings in at a particular location here. So again, a really informative database and a model here that you can actually use. Yes? I can go back. There it is.
I don't know if it's a matter of that there's less points at higher latitudes, but the range of values seems to be much wider as well. Does that hold? Does it increase like the range of values?
The range of values at higher latitudes tends to a little bit, because when we go to also to higher latitudes, we also get to areas that are coastal and they're not affected as much by the cold storms than as you go to continental interiors where they get manifest. So the higher the latitude is, the more variation you actually see in the isotope variation, whether it's oxygen or hydrogen. So yeah, your eyes are not deceiving you. That's basically, yeah, you're looking like you want to ask a question. Okay, yeah. All these data are in your notes. If you don't go back and stare at them, you're fired. Because you're going to, that's why we give you the notes, so you go back to them. Again, we can go on some isotope field trips or road trips here, and this is kind of cool because in a plot like this, we can see a bunch of different things at play. So this black line that's drawn across this plot here really represents, if we go on a road trip from coastal Alaska, we stay kind of at the same latitude. Then we go to continental interior. Again, we don't change latitude too much. And then we go from that northern latitude to a southern latitude. And what's plotted here is here's the hydrogen isotope composition along that trajectory. So you can see that we go from values close to minus 100. We move more continentally along a particular latitude, so we get more negative. We stay kind of negative for a while, and then we show an isotope excursion back to much more positive latitudes as we move to those southerly, more Caribbean locations here. So this is really cool because there's a lot of people in this paper that was published a decade ago. Keith Hobson was really interested. He's got all these birds that he works up here. Keith works for the Canadian Wildlife Service, and a lot of his birds that come to Canada every year come from here. And so Keith he wanted to know what this isoscape looked like. He goes, I want to know what all my birds are seeing in terms of water sources along the way where they might stop and drink. Some of that water gets incorporated into their body. Some of that body water gets incorporated in their feathers. And I want to know what that looks like. So Gabe, let's make some isoscapes so we can interpret what our birds are doing as they fly from southerly to northerly latitudes and back. So this has been a very important kind of information for people that are working on migratory animals and birds in particular. This is a paper that Gabe and Keith Hobson and a few other people worked on together. And again, all of these effects are kind of being manifest at once. We've got latitudinal effects, altitudinal effects, and continentality that kind of go into play, explaining some of the variation that we see in these different isopleths of isotopes across this North American isoscape here. Back to your question, source effects are also very important. And in a study that was done by Ron Amundsen, this really came to roost in a very, very important way. Ron was working out here in the middle of the continental United States, and he was working on pedogenic carbonates, all right, carbonates, and he was measuring carbon and oxygen isotopes in the carbonate that was being accumulated on the soil peds that he was collecting at that location right there. And he started analyzing. The carbonates get laid down almost like tree rings. You can see this little rind forming, and they just keep forming as the carbonate is forming and the new water comes in. And he got these massive isotope excursions, and he was in this continental interior here, and he went, what the heck is going on here? I kind of have an expectation that my water that comes out of the Gulf of Alaska is the primary water source for my carbonates. And what he had not realized is that he was working on carbonates that were pretty old. They were about 5,000 or 6,000 years old. And when he went back to some of the information that other people had been working on, he realized that 5,000 or 6,000 years ago, the monsoon injection out of the Gulf here was a lot stronger than it is today. And so there was a secondary water source that was actually influencing the oxygen isotope composition of the water, which got incorporated into the carbonate that got laid down on the pedogenic carbonate. And so when he was looking at each one of those layers, sometimes the oxygen looked like a northerly storm, sometimes it looked like a southerly storm, and he was absolutely right. It was all about the source areas of the water where they were coming from. And one was a warm source and one was a cold source. So right back to your point, that source can be really important, play a very important role, not only on the precip, but the things that get formed out of the precip, the carbonate, the hair, the leaf, whatever has you. So source effects can be very important. If you work in an area where different sources of moisture could be important, you got to be able to characterize this for your site. Otherwise, it can really frustrate you when you go in and you look at your samples and you go, I got a flyer here. And it's actually not a flyer. It's probably something that is being explained by a different source of moisture that you probably just didn't measure.